Hi, and welcome to this top-level overview of procedural systems created to support a decade of Marvel's Spider-Man games at Insomniac. But before I start, I'd like to thank Side Effects and Brady University and say that this is an amazing room. Like I said, my name is Xray Halperin, and I'm a senior technical artist in the core engineering group at Insomniac Games, and thank you for spending your time with me today. Instead of taking pictures of these slides, because I know some people like to do that, I encourage you to take a picture of this slide and download the PDF. That way you can actually just pay attention to the show and not try to get all the pictures. Okay? All right. At Insomniac Games, the technical art department works within core engineering to provide procedural solutions for authoring open world games. We use a proprietary game engine and create custom-made solutions. Most of the data is pre-baked, not generated at runtime, and across multiple Spider-Man games, some systems see reuse, some evolve, and we invent new ones along the way. Python and Houdini provide the framework for much of the procedural content. The procedural tech art team grew from 1 artist in 2013, doubling to 2 artists in 2016. The use of procedural techniques has grown across Insomniac Games as various departments have adapted and adopted tech art workflows. Some groups, such as VFX and character effects, actually began developing their own tools and techniques with the support of the tech art group. Most of the open world of Marvel's Spider-Man is authored or edited by a procedural system at one time or another. All the Marvel Spider-Man games are streaming games. A streaming game is a game that constantly loads or streams content based on the player's traversal. The streaming architecture of our games informs how we approach solutions to authoring the open worlds. The open world environment of Marvel's Spider-Man is divided into 726 tile regions. Each tile region is defined by several zone files, which are JSON that references the assets within a given tile region. The tile regions become the basic unit of work for processing data. For example, a tile could be a work item in a PDG network. Here's a video of the full streaming system in action. For Marvel's Spider-Man 2, high-resolution assets load in near the camera, while the imposter and hibernation systems handle distant geometry beyond 256 meters from the player. The high-resolution assets and their LODs are made of many model instances stored in a prefab, while the imposters are a single mesh with projected textures stored in an atlas. The high-quality assets stream out and get replaced by their linked imposters at a distance. Once again, I'll make the point that this streaming architecture informs how we approach solutions for authoring the open worlds. Here, the imposter system is turned off, so we can see the streaming content clearly. The Marvel Spider-Man game constantly loads the tile the player occupies, as well as the 9 tiles around the player. As the centroid of an asset gets to the edge of the streaming area, the geometry reaches its lowest streaming LOD, textures reach the lowest MIP, and the content unloads and is replaced by the distant imposters, which are always stored in global resident memory. This JSON snippet represents a streaming region for a single tile. Each streaming tile region contains references to the zones, prefabs, volumes, markup, and gameplay relevant to that streaming region. In order to analyze and modify open world game content, I wrote a pipeline to import game data from our proprietary engine and level editor into Houdini. When loading game content into a DCC like Houdini, the first step in much of the Insomniac Games procedural workflow is to construct a point cloud from the zone data. Python scripts parse the JSON from the zone files and recurse through all of the references. We use a custom Houdini digital asset to load JSON containers and build a point cloud representing the pivot of each model instance within the zone, read the attributes from the JSON, and flatten the transformations into world space. This point cloud setup is sort of like a Swiss Army knife for many of the subsequent tools. The orientations derived from the attributes on the point cloud align the incoming model instances. Technical artists can then begin reasoning about the geometry to create even more procedural tools. Let's have a look at where these tools began on the first Spider-Man game for PS4 in 2017. We'll start with the open world authoring. To build the open world of Marvel's Spider-Man, initial buildings are procedurally created from primitives and polyline volumes in untiled reference art zones. Starting from a procedurally generated gray box layout, artists refine building shapes by modifying or adding primitives and polylines. The gray box version of the open world gets processed by procedural systems to instance models from building kits onto the faces of the layout shapes to create building prefabs. Architectural component models and markups such as swing hint volumes, ledge path curves, and other markup are stored in edifice prefabs. The rooftops may be custom generated or created from multiple instances of rectangular grids. Much like 2D HTML markup on a web page, Marvel's Spider-Man is full of 3D markup defining how the player interacts with and traverses the world. The markup is procedurally generated, however, missing or incorrect markup on atypical architecture often requires hand markup by artists or designers. Types of markup include swing hint volumes, ledge path curves, wall crawl collision polys, and wall crawl blocker volumes. The open world of Marvel's Spider-Man consisted of 8,300 buildings. Creating the street layout requires defining a set of curves to mark where the various asset types, such as highways, boulevards, streets, and alleyways exist. We start with the island outline of Manhattan. From these lines and curves, we generate streets, sidewalks, gray spaces, and seawalls. The naming convention of the curves informs the system of street metrics, directions, and style choices. The resulting models and data are used by other procedural systems that place encounters, vignettes, props, pedestrians, and vehicle traffic. Ground modifiers affect how the environment is constructed. This yellow overlay represents the ground modifier zone. The ground modifiers cut, deform, modify, or add materials to the streets and sidewalks. The procedurally generated ground defines the key spaces and landmarks. Each 128-meter tile gets sliced into 16 models so that each model is a manageable slice for physics and other systems. Here we can see a single streaming tile of the ground cut into 16 models and saved in a prefab along with street line and crosswalk models created by procedural prop systems. The ground prefabs often contain ground props for flat items and decals. In keeping with the expanded size of Marvel's Spider-Man 2, the road curve network increased in size to accommodate Brooklyn and Queens. Procedural techniques were used to help define the audio environment in Marvel's Spider-Man. We used a procedural system to reason about the geometric layout of Marvel's Manhattan and place volumes where needed. The emitters along the seawall edge of Marvel's Manhattan defined how the audio boundary blended between the island and the water. For the reverb volumes within Marvel's Manhattan, as a proof of concept, the audio department laid out the open world audio volumes by hand for a single district. The work took 2 or 3 days, so a procedural workflow was required to author and update the open world audio volumes efficiently. We created a pipeline to reason about the street curves and bounding boxes of the building prefabs in Marvel's Manhattan to generate audio reverb volumes along the streets and in between the buildings. The street curve naming convention and volume size informs the reverb and delay presets for each volume. We could update the volumes at any time the open world layout changed. Finally, all the audio volumes are written out to the relevant streaming tile regions. For Marvel's Spider-Man 2, we increased the building height thresholds and added reverb volumes to Brooklyn and Queens. Using similar techniques to the audio volumes, we procedurally place spawner volumes for pedestrians, parked cars, and long-range pedestrians to maintain the illusion of pedestrians going off into the distance. The combination of pedestrian, parking, and long-range spawner volumes keeps Marvel's Manhattan bustling. The same road curve network also drives procedurally placed pedestrian and vehicle traffic controls. After placing pedestrian spawner volumes on sidewalks, we wrote some tools to create a network of paths connecting corner to corner on each sidewalk and around bus and subway stops, as well as the occasional hand-authored path. By parsing the curves in Houdini, we author JSON with traffic node assets and the phases for each link between the nodes. The color of the debug visualization in the level editor changes based on the phase of the traffic lights. This complex area features both pedestrian and vehicle paths intermingling. All of the street signs in Marvel's Spider-Man games are procedurally generated from the same curve network that drives the ground generation. Let's have a look at the intersection of Kingston and Park Avenues in the Brooklyn, Queens area of Marvel's Spider-Man 2. While iterating over each of the curves representing a street, we generate a texture for each unique street name. This view of the Insomniac Asset Vault shows a collection of street sign textures. Each traffic signal instance starts with a blank placeholder for the street names, which gets an override indicating what street name texture to apply. As Houdini iterates over each intersection, it looks for the nearest traffic signal, computes the orientation of the street signs, matches the direction to the street name, and applies the texture as an override to the correct sign instance. For Marvel's Spider-Man 2, we added all the street names to the expanded areas of Brooklyn and Queens using the same system as Marvel's Spider-Man and Marvel's Spider-Man Miles Morales. This JSON snippet represents the texture overrides on a traffic signal prefab. The override is procedurally generated by a Python script running in Houdini and added to each traffic signal instance in the open world. The term imposter often refers to the representation of geometric assets using a texture map projected onto a polygon. Massell and Shirley described view-dependent and view-independent imposters in their 1995 paper, Visual Navigation of Large Environments Using Textured Clusters. For view-independent textures, the high-resolution asset is captured from several cameras arranged around a hemisphere. The texture projection is driven by selecting the best match relative to the viewing angle of the render camera. This results in many textures per imposter. The number of textures may be very large when using view-dependent or independent techniques. Billboarding techniques lack the parallax required to handle the fidelity required by modern open-world games. Simple texture projection does not handle reflective or emissive surface properties. By combining all of the model instances that make up a building prefab into a single poly-reduced mesh and capturing a texture atlas from all of the visible sides of the building, the Insomniac engine only needs one draw call to render the distant imposter. When converting a prefab of many model instances into an imposter, we start with the lowest level of detail. We load it into Houdini using the point cloud instancing method mentioned earlier, which gets assembled and poly-reduced in Houdini using a few techniques to remove interior detail but preserve the silhouette. In the Insomniac engine, we capture the imposter geometry and generate an orthogonal texture atlas. The textured imposters on the left, the textured low-lod is in the middle, and the untextured imposters on the right. Prop elements such as antennas and air conditioning units, which contribute to the silhouette, are tagged separately and handled by a distant hibernation system. With each Marvel's Spider-Man title, Insomniac increased the fidelity of our imposter system. Imposters in Marvel's Spider-Man Remaster used the same texel density and resolution as Marvel's Spider-Man Miles Morales. For Marvel's Spider-Man Miles Morales, we bumped the texel density. However, we had to support different texel densities depending on the target platform, PS4 or PS5, since it was a cross-generational release. For Marvel's Spider-Man 2, we increased the texel density again, and I think the results look pretty good at multiple times of day. For Spider-Man 2, we matriculated the imposter system away from Houdini and built a workflow directly into the Insomniac level editor. Please check out Scott Kircher's GDC talk, Applied Mesh Analysis, Automating Distant City LODs in Marvel's Spider-Man 2 for a deeper dive into the IG imposter system. I'm sure it's on the GDC vault already. The vignette encounter system workflow is implemented in Houdini. Each encounter placement module contains operators used to place vignettes based on rules and metrics. The first input contains sparse data about the roads and environment and collision data. The second input provides feedback about the location of previously placed encounters that have to be considered in the loop. We exposed a limited interface for populating the open world with encounters. The module computes all the locations where the placement metrics are satisfied. It filters out occupied and excluded locations and culls to the desired density or count. Here's the distribution of an arrest vignette in Chinatown. That's criminals being arrested. The simple placement rules put them at least 150 meters apart on alternate sides of the street and greater than 9 meters from a crosswalk. The default prefabs for vignettes are fully functional in the game solely with the correct placement. We run a procedural analysis of the bounding boxes of the vignette content against the open world geometry to detect possible collisions. We mark any assets with suspicious intersecting geometry, and a human evaluates each suspicious vignette and adjusts the vignette content to fit the environment. Finally, we can see the vignette in the game context. The procedural tools for light grids and light probes remained fundamentally stable between all of Marvel's Spider-Man games, and you can see that content in my 2019 GDC talk. For Marvel's Spider-Man 2, we increased the number of light probes from a 2x2 grid per tile to a 3x3 grid per tile. The light probes in this image are a little hard to see, but they're represented by the red spheres there. For Marvel's Spider-Man 2, we added consideration for foliage and computation for light grids, and we increased the fidelity of reflections by increasing the number of light probes per streaming region from a base of 2x2 to 3x3. And we added sets of low, medium, and high altitude light probes. Again, the probes are represented by the red spheres in this image. It wouldn't be a Marvel's Spider-Man game if I didn't talk about Puddles. For Marvel's Spider-Man, we procedurally placed the puddle assets and their splashes based on vertex color thresholds of the underlying geometry. For Marvel's Spider-Man 2, we procedurally moved all the puddle assets since they're now integrated and controlled directly by updated ground material graphs. We continued to develop procedural systems for Marvel's Spider-Man Miles Morales, a cross-platform game for the PS4 and PS5. The playable area slightly increased. We used procedural systems for several workflows, including a full reskin of Marvel's Manhattan to change the seasons. Marvel's Spider-Man Miles Morales is set during the winter and required updating the environment of Marvel's Manhattan for the holidays. Most of the objects in this Houdini network view represent various workflows needed to generate procedural content for Marvel's Spider-Man Miles Morales. A big part of changing the season for Marvel's Spider-Man Miles Morales from fall to winter was adding snow. Vertex colors were added to the ground to drive shader components. The vertex colors controlled the directionality of ice on the asphalt and sidewalk. Other procedural systems measured the curbs and placed snow mounds on reasonable metrics while avoiding driveways and corners. A similar system placed snow mounds on the lane lines. In this visualization, we'll look at a single tile in Greenwich Village called M35. M35 is a typical streaming tile made up of some street-level terrain with various streets and sidewalks, as well as some mid-rise buildings. I'd like to point out tile M35 is my personal favorite test tile in the game. Why is that? It's because that's where Doctor Strange's Sanctum Sanctorum is in Marvel's Manhattan. And here's the final tile as it appears in the Insomniac level editor. The road and curb snow assets are prefabs made of several model instances and built to metrics of 2, 4, 8, and 16 meters. The final assets are gathered in a collection and displayed here in the Insomniac Asset Vault. To place the snow, first I isolate the terrain, I isolate the edges of the curbs, I trim the isolated curbs back a bit from the corners to keep things from piling up in the accessibility ramps, and I trim away areas near driveways or subway entrances. After measuring the resulting curves, I select appropriate elements from the collection and instance them along the curbs. I use a similar system to add snow skirts around the bases of buildings, instancing different snow assets from the collection as appropriate. And finally, placing all of the snow assets into the streaming tile region. For Marvel's Spider-Man 2, the same system that generated snow skirts around the buildings was repurposed with a new model collection to generate the sand skirts around buildings for the aftermath of Sandman's assault on Marvel's Manhattan. We used vertex paint colors to drive the directionality of the ice on the asphalt. The vertex colors are visible in this GL rendering of the geometry color attributes. This video displays a tight integration between Houdini and the Insomniac level editor. Houdini's on the left and the level editor's on the right. As the ground geometry with painted vertex colors is saved to disk, the binary data is built on the fly and ingested directly into the level editor. On the left, an artist is adjusting the red channel of the vertex colors, which control the directionality of the icy road surface texture. The art direction called for directional streaks on the roads with an omnidirectional noise pattern in the intersections. Marvel's Spider-Man Miles Morales also introduces a new enemy, the Underground. This tech-powered faction jumps from rooftop to rooftop, chasing Spider-Man with 3D pathfinding assisted by navigation clue markup procedurally generated in Houdini. The procedural navigation clue placement sets the path endpoints in satisfactory positions. Raycasting finds a clear path from one endpoint to another through an intermediate waypoint. The system tries to generate at least one path to each neighboring rooftop or sidewalk. This allows enemies to chase Spider-Man around the city. A combination of the edge markup and roof geometry drives possible paths for valid jumps from roof to roof using some baseline heuristics such as vertical and horizontal minimum and maximum distance and maximum angle using a dot product. Let's look at our old friend tile M35. Extracting the ledge markup and combining it with the roof and building footprints allows for reasoning about the possible paths that meet our criteria. I further cull the available paths using various heuristics and rules, lather, rinse, and repeat for all of the streaming regions in the open world. Here's the final raw nav data clues in the level editor for tile M35. While the lines that connect the start and ending points make it look like some of the navigation clues are penetrating walls, there is a midpoint helper volume that allows the underground enemies to jump in an arc. For Marvel's Spider-Man Miles Morales, we introduced a spline to model tool. The tool exposed controls for a Houdini digital asset to artists using the Insomniac level editor. Cross-section controls and placement options control instancing or sweeping geometry along the curves. A Python-based importer dynamically creates attributes for the properties added in the editor and sends them to Houdini. The tool can place individual assets or select from a collection of assets for instancing. This is one of the first examples demonstrating the spline to model tool used on Marvel's Spider-Man Miles Morales. Various assets are instanced or swept along the green spline curve. From this vantage point, we can see a collection of different trees instanced along a path in Central Park, where we placed a paved path beneath the trees along with some pedestrians who appear to have lost their heads. Artists and designers invented all sorts of different ways to use the spline to model tool, including authoring these off-ramps using curves and a freeway model cross-section. For Marvel's Spider-Man 2, we added a Houdini integration directly into the level editor, which eliminated the need for a specialized spline to model tool. The Houdini integration allows artists to use Houdini HDAs to directly author game content in the context. This was used extensively for freeways and train tracks. Marvel's Spider-Man has 720 tiles in the open world. Miles Morales had 735 tiles. Marvel's Spider-Man 2 has 1,794 tiles in the open world, and the overall playing area nearly doubled. For Spider-Man 2, Insomniac introduced a new system to help manage persistent environment effects called the load hint system. The load hint system was an improvement over our older overlay system and used extensively, the overlay system was used extensively in Spider-Man and Miles Morales. Marvel's Spider-Man had a 3-act narrative. Over the course of the game, Manhattan devolves from a bustling metropolis to a city on the verge of collapse. This transition was controlled with overlay zones, which could load and unload appropriate artistic set dressing. Overlays were not well supported by imposters. It was kind of ad hoc and relied on some fragile naming conventions and manual work to keep the overlays up to date. There was no central system to find all the possible overlays in the game. For Marvel's Spider-Man 2, we introduced the load hint system. This JSON snippet represents dynamic enums for load hints. Load hints require dynamic enums to specify the in-game world state. In this example, the load hint controls how much sand is left over in the open world after Sandman's attack and subsequent recovery. The load hint system replaces overlays for many tasks and is well supported by imposters. Load hints are used to control when prefab actors should be loaded and shown in the game. Artists can then utilize those dynamic enums to mark up any prefab actors found in zones to indicate when those items should be shown. This allows for several dynamic, consistent, and persistent world states in Marvel's Spider-Man 2, supported by all of the overworld systems. Another example of persistent environmental effects in Marvel's Spider-Man 2 occurs during Venom's symbiote takeover of Manhattan. This video shows an example of the symbiote world state as well as matching imposters for the tile region in load hints. Clearly the imposter is quite decimated, but that's by design since imposters are meant for distant views. For the symbiote takeover, we instanced about 20 symbiote assets along a curve, and we added a material graph made of vertex flow data and normal maps baked from Houdini. The symbiote taker of Marvel's Manhattan combined load hints, imposters, and procedural environment art. The core rendering team added a native color volume asset to the Insomniac engine. Color volumes are intended to provide a way to apply large-scale unique masking. They function kind of like invisible decals, projecting textures onto underlying geometry. While decals are basically projected textures, color volumes, unlike decals, may be sampled by materials. The projected color values are not directly visible in the scene. Instead, material graphs read the color values at their point in space and use the resulting value to drive logic in the graph. They serve as similar purpose to painted vertex colors, but offer some key advantages. Color volumes are not dependent on the underlying tessellation. They work fine across different LODs, and the information isn't lost if the underlying geometry changes. Color volumes provide a more straightforward workflow for running physical simulations in Houdini, capturing the result in a texture, and then applying it to features of the environment materials, such as dirt, grime, and weathering. The texel density of color volumes is low, maybe 1 to 4 texels per meter. The color volume textures do not have enough resolution to store significant visual details by themselves. Here's a plain old wall we want to apply a color volume to. In the material shader, a color volume node samples the color volume at each location and creates an interpolation between 2 base texture maps. Here's the effect of the color volume only and the blended effect on the asset. In a weathering texture, the red channel might look something like this. And when applied to building prefabs in the open world, we can view the raw results of the color volumes. Depending on the use case, each color channel can drive some material properties such as weathering, damage, grime, dirt, or wetness. We assign a color volume per direction to each building prefab and 1 color volume to the ground prefab in each tile. For Marvel Spider-Man 2, we added an asset tagging system. For the modular building kits that make up the bulk of the buildings in Marvel Spider-Man 2, we used asset tagging to support downstream procedural systems. An auto-tagging Houdini digital asset using Python searches for predefined asset paths for building kit pieces that match known search strings to derive the final tags. A point cloud is created to hold the asset attributes so that downstream processes can work with the parsed data as if it were geometry. We import each model in turn, validate the content to make sure the file name's parsable, and that the geometry has all of the features expected. Finally, the HDA generates the metadata required by the Insomniac Asset Vault for tagging. The metadata from the asset tags may be used by downstream processes. For example, this building variation digital asset in Houdini, which swaps matching building kit pieces from one prefab into a new prefab based on the building kit style. And let's wrap up with a word about webs. Marvel's Spider-Man and Spider-Man Miles Morales webs used some simple geometry attached to a skeleton rig with a shader to provide a web look. For Marvel's Spider-Man 2, we explored higher fidelity options using new geometry which would attach to the existing web rig. To generate the web cones, we added trails to a particle system, manipulate it by adding some twists and noise, and skin the results. For the secondary attachment points, we create another particle system from the endpoints of the first, trail the particles, skin them, and merge it all together. Finally, a knotted attachment point is added to the base of the web cone. To develop both the web cone and the web thread knots, we used an editable spline ramp and expressions to drive coiling. Starting from a basic spline shape like an expanding spiral, an artist adjusts the scaling, amplitude, and frequency of the line segments, then skins, adjusts, poly reduces, and UV maps the final geometry for export to the engine. The web cones were added to the stealth web lines, but scaled to be flat. Here's some examples of the web line knots, as well as the venom webs. And some final love in the material gave the webs a polished look for the final game. Thwip, thwip. I'd like to thank the Insomniacs who helped with this presentation: Sean Applegate, Matthew Bennett, Abdul Bezradi, Matt Bullister, Cullen Carnes, Harrison Eilers, Mike Fitzgerald, Al Hastings, Phil Hunter, Ashley Jennings, Jeraine Jackson, Scott Kircher, Paul Martin, Jake Parmley, Elon Ruskin, David Santiago, Stephen Skidmore, and Jay Twasson. It's audiences like you that make presentations awesome. Thank you very much. While I take some questions, I want to leave you all with some fun facts about Marvel's Spider-Man 2.
Yeah, so I had a question because you showed the vertex painting of the snow on the cross sections, and then after that you talked about color volumes. Is there a reason you didn't use color volumes for the cross sections, or was it nothing specific?
Color volumes were a new feature that was added for Spider-Man 2, and we basically replaced a lot of the stuff that we were doing with vertex colors in the previous games with the color volume technique. We found that it was, vertex colors have a lot of issues, especially if you need to change the LODs, they get popping and stuff like that. And color volumes just get rid of a lot of those problems. So we moved over in favor of color volumes for Spider-Man 2.
A great presentation, thank you. The imposters you showed still had relatively high polygon count. Makes me wonder, when you overlook the city and you see all 8,000 buildings, what is the polygon count for the screen at that point, approximately?
I can't give you the polygon count for the screen, but what I can say is that the geometry, which is a fairly low LOD, considering the quality of the starting artwork, and the lowest MIP of the textures for the entire city on Spider-Man was about 800 megabytes. And on Spider-Man 2, it's just over a gigabyte. It's highly compressed. We highly optimize it. All the data is quantized, so we get rid of a lot of the floating point information. And it's a very low-level system in the game. It's also leveraged for a bunch of other systems because it's always in resident memory. When you go to you hit the D-pad and it shows you the 3D map of the city, that's actually the same imposters. So there's no load time from going to the game to that map. Additionally, we use the imposters for cascaded shadow maps. So if there's it's sunset and the sun is low in the sky and there's a tall building way off in the distance, that the imposter of that tall building is what's casting the long shadow across the city.
Hello, from the back over here. Thank you for the talk, really impressive. The amount of complexity is what my question is related to. It's super awesome that you showed the process in 8 years or so, of how it evolved. Is there a rule that you follow, a high-level rule in terms of how you structure these tools to manage the complexity of it? Like the part with the initial tool, which just gives the data for all subsequent tools. Are they allowed to, basically, is every secondary tool a self-standing one where it does one concrete thing and it's not allowed to communicate with other tools, or is it
It depends on the system. Some of the systems are highly integrated with each other, and some are kind of standalone. For example, the part where I'm generating street sign textures, right? It's relatively standalone, but it reads that curve network. So if you were to update that curve network, you could regenerate all of the street signs, for example. The imposter system is again, once the city is generated, it reads that data in. Right? But if the city were to change and you were to regenerate the imposters, it would be fairly automated. There's a little bit of human on Spider-Man and Miles Morales, there's a little bit of human intervention involved. As I mentioned, we kind of changed how we did it on Spider-Man 2, and it's a fairly automated back-end system now. You had a question, Mayor?
I've got a question over here. Hey, Xray, thanks for the talk.
You're welcome.
I'm wondering, there's a lot of mention of procedural systems that are then being overridden or manually authored later by the artists. Are the artists generally able to do all of this from the Insomniac Games engine? Or is there a lot of artists that are slowly getting into Houdini, even if that's not their field?
Well, so once an artist starts really changing assets around, we have to be careful because it's easy to kind of stomp over that with a procedural system. A lot of that comes down to like either using naming conventions or just talking to people, communication from person to person. And it's a hard problem to solve. Like where do you draw the line between procedural and kind of hand-authored stuff? I don't think we've really cracked that problem per se. And ultimately, it kind of just really comes down to communicating between the artists and the tech artists about what's in play at any given moment.
Okay. Is there one more question? Okay.
Thank you for the talk. I saw on one of the earlier slides where you show one of the tile, and you seem to have divided that tile into even almost like irregular shaped subsections. So what drives, like how do you decide what shape to cut it to?
Well, David Santiago wrote that part of the system, and we try to do it in a way where we're hiding the seams. So we try to like cut it along the sidewalk curb or where clear things are. And sometimes those are on odd diagonals or something, and the vertex splits just end up being a little bit jagged, but it's fine, although at a deeper level, sometimes we run into issues where we're splitting verts and like we end up with a slight displacement or something. So there's like a whole bunch of other code that's been written to kind of deal with when the vertex splits don't line up with each other. But it's a matter of like where the vertex splits happen in a procedural system, which we've sort of given up a certain amount of control with, but we try to drive it by, where the lane lines are in streets or where the street to sidewalk transitions happen and things like that.
Thank you.
Okay, thank you very much. That was a wonderful talk.
Thank you.